Back in 2012, some MIT researchers published a paper in Energy and Environmental Science entitled Solar Energy Generation in 3 Dimensions. They made some fascinating points about how nature rarely collects sunlight by moving and aiming photoreceptors directly at the sun. The majority of time, sunlight is collected at random angles. The leaves on trees, or needles on pine trees, for example. So the researchers noted that when we build solar collectors, we always try to maximize the efficiency by carefully aiming the collector directly at the sun. Sometimes we even actively drive the collectors to constantly track the sun across the sky. These researchers asked the question from a biomimicry perspective. What would happen if we followed suit and placed our solar collectors at random angles to the sun? This paper and its interesting results were only recently brought to my attention and is of great interest to me, seeing as how I've got about 10 kilowatts of photovoltaics I'll be setting up here at the Tech Valley Science Center. So in this Science Short, we're going to dive into what these researchers did, look at the results, and conduct our own experiments with 4 different solar panel arrays. Researchers called their work 3D photovoltaics, and I've included a link to the paper in the description. They first conducted a whole pile of computer simulations and then built multiple solar arrays and tested them in real-world conditions to verify or refute the computer simulated data. Interestingly, they put their experimental arrays on the roof at MIT and waited weeks before they finally got a sunny day to really compare their different arrays. It just so happened that when they set up their experiment, they were plagued with a couple of weeks of cloudy conditions. As it turns out, this was for the better, as it led to a bit of a serendipitous discovery. When they went back and looked at the data collected during the cloudy weeks, the 3D photovoltaics outperformed the flat solar panels that were aimed at the sun. In fact, they claimed efficiency improvements of 2 to 20 times that of flat solar panels. By far, the biggest improvement over conventional flat panel solar collection was during poor light conditions, when it was cloudy or when the sun was low on the horizon. Now, I hate to say it, but the report itself was pretty confusing because they were trying to take into account the photovoltaic surface area and its footprint area. This is all important for multiple reasons, which they discuss in the paper, and these footprint areas change dramatically depending on how you build the array. They certainly were careful to take everything into account, but in doing so, they went all over the map in their reporting. I was pretty sure they were onto something here, but I wanted to nail down exactly what they discovered before I set up my own photovoltaic array. So I set out to conduct my own experiments. You can see here, I replicated their accordion style array, but I made mine only one-sided. On their arrays, they had solar cells in the back of the accordion as well. I used 8 individual cells, all wired in parallel. I also made 2 flat panel arrays, each assembled with the same number of parallel wired solar cells to have a more direct comparison. One of the flat panels was set on an angle and facing due south, and the second flat panel tracked the sun on one axis, set at the same angle as the first. I put them both at 45 degrees as this experiment was going to be fairly short term, perhaps only a couple of weeks. And at this latitude and this time of year, that is the angle of the sun over the horizon at high noon. In all cases, I put a 1N4004 diode on all cells to protect against parasitic losses. This was mostly for the accordion array, as some of the cells will have less light shone on them than other cells. So the cells in darker conditions would produce a lower voltage than the brightly lit cells, and so current would backfeed through the shaded cells because of the voltage differential. Putting diodes on all solar cells blocks this from happening, and so to ensure all three arrays had electrical characteristics that were as matched as possible, I ran all cells in all arrays through a diode. The accordion-style array was mounted vertically for the first experimental run. Then it too was set on an angle matching the flat panel arrays for a second experimental run. To minimize the casting of shadows, the structure for the accordion array was built on the back. But on all arrays, I endeavored to keep the backs of the solar cells as exposed to the air as possible for cooling. I did this because cooler cells produce more energy than hot cells. I also spaced out the arrays to try to keep the arrays from casting any shadows on the other arrays. I hooked each of the panels up to their own resistive loads, and this fed a pair of series resistors, making a voltage divider which was connected across the load resistor. The voltage divider was needed as the panels were putting out 6 volts or more, and I needed to read the voltage with a microcontroller that had 3.3 volt analog to digital conversion. I monitored this voltage with a cellular IoT microcontroller board, a particle electron. The electron drove the servo for the sun tracking array and took a voltage rating on all 3 load resistors every 10 minutes. The electron would send the voltage readings over the internet via cellular data to a Google Sheets spreadsheet. This enabled me to collect and use the data and later on even plot it on pretty charts and graphs. I placed the entire assembly on top of the roof of the Tech Valley Science Center, which the builders specifically designed and constructed with solar energy collection in mind, so there are no trees or shadows from the south-facing side of the building. I let the experiment run and kept track of sky conditions throughout the days the experiments were running. If you recall, I mentioned I did 2 runs, one with the accordion array vertical and one with it angled so its long axis was perpendicular to the sun at high noon. One of the things the MIT researchers emphasized, and I think this is a very significant point, is that the 3D photovoltaics had a considerably higher average power production. In other words, a static photovoltaic array produces very little power in the early morning and late evening because the sun is low on the horizon and the sun's rays are striking the panels at an extreme angle. At noon, the sun's rays are hopefully striking the panel perpendicularly, thus hitting maximum power production. Obviously, the whole point of a tracking array is to hopefully keep the panel perpendicular to the sun at all times to maximize power production. When it comes to 3D photovoltaics, the whole point is that the sun's rays will never be perpendicular to the panels. So, of course, the peak energy production of 3D photovoltaics is lower than the aimed flat panel array. However, a solar cell always has a somewhat reflective surface. So flat panel arrays unavoidably reflect some of the sunlight, bouncing it off the surface and losing it to space. With 3D photovoltaics, the individual cells were usually angled towards each other. So light bouncing off the shiny surface of one cell reflects onto another nearby cell, where it is collected and converted into power. The MIT researchers noted that the 3D photovoltaics really performed well in low light, cloudy conditions or times when the sun was low on the horizon. This makes sense actually because in cloudy conditions, the incoming light is diffused and not directional. My results were quite different than the MIT researchers, but yet I may have inadvertently obtained similar results by completely different means. So let's take a look at some of the results. Now here's a chart from day 1, which went online around 1100 hours. It was a particularly beautiful sunny day with some clouds moving across the sky later that afternoon. The yellow line with the arrow points is the readings from the sun tracking array. The red line with the box points is the readings from the fixed panel array, and the blue line with the box points are the readings from the accordion array. The numbers on the Y portion of the graph are straight readings from the analog to digital converter, which was 12-bit. So I was only concerned with the panel readings relative to each other. The maximum number you can get is 4095, which is 3.3 volts. So if you so wish, you can convert the A to D number into an actual voltage by first coming up with the multiplication factor. Divide 3.3 by 4095 equals 0.0008058 volts per bit. So for example, a reading of 3000 on the A to D converter would work out to 3000 times 0.00808058 equals 2.417 volts. Because the MIT researchers focused heavily on the overall average power production, and I agree that is important, I also calculated the daily averages for each of the panels, which are the straight lines across the charts with the same color scheme. So you can see that on this mostly bright sunny day, the accordion panel underperformed compared to the others, and by quite a bit. The fixed array produced an average of 13% more power, while the tracking array produced 19% more. It should be noted, however, that this day was missing in the entire early morning when the sun was low on the horizon and when the 3D photovoltaics are supposed to perform best. And also bear in mind that this was when the accordion array was set up vertically. But as you look at the graphs of all 2 weeks, you'll see that the 3D accordion array underperformed in all conditions, especially during the first 7-day run with the accordion array oriented vertically. The other two arrays outperformed it by typically 20% to sometimes as high as 50% more power production. At the end of 7 days, I felt I had gotten enough variety in conditions, so I tilted the accordion array backwards to 45 degrees and started the second round of experiments. This showed a drastic improvement in power production, where one cloudy and snowy day, its daily average rivaled the power production of the other two arrays. Day 10 was one of the unusual cases where mid-morning I had noticed that the tracking array had failed. Basically, the batteries on the tracking servo had died. So I replaced the batteries and got it up and running again. So for that day, I removed all data points from before 8:45. When I got the sun tracking panel working again. But for that day, the accordion array's average was challenging the fixed panel array, the fixed angle array. On day 14, something unusual happened for which I have no explanation. The day started off with the tracking failing again, and I fixed it one more around 0900. So all data points from before 0900 were removed. However, even though it was a beautiful sunny and cold day, right around 1700 hours, the power production on the fixed angle array dropped off pretty dramatically. I thought perhaps it was a shadow from the trees to the west of the property, but I didn't see this drastic power drop at this time on any other day, and the accordion array was right beside it. And obviously it didn't experience the same issue, as it was producing much higher power than it usually did at that time of the evening. In fact, right around here, the thumb screw had become loosened on the base of the accordion array, and it fell down flat, facing straight up into the sky. It was still producing more power than the fixed angle array. Even with all of that, the accordion panel still outperformed the fixed panel array over the time period of data collection, producing an average of about 4% more power. To be honest, the accordion array was a bit of a disappointment. It did not live up to the expectations I had after reading the MIT paper. Nevertheless, some surprises came out of all this with regards to the sun tracking array and the fixed angle array. I expected the sun tracking array to outperform them all by quite a bit. Instead, the fixed panel array was often right on par for daily average power production. In fact, for several of the days, the average power production lines are right on top of each other, differing by only a millivolt or two. And on partly cloudy day 9, the fixed angle array outperformed the sun tracking array in power production by about 3%. Now, this all ties back to a serendipitous discovery I made right off the bat on the morning of day 2, which seems to tie all of this research together in an unusual way. On the morning of day 2, I noticed that the tracking servo had failed. The tracked panel was at a steep angle to the rising sun, probably about 20 degrees or so. The servo batteries had died in the middle of the night, so I climbed up and replaced the batteries, getting the tracking fully functioning at about 9:35, and the tracking panel snapped to attention perpendicular to the sun, just like it should. The particle was happily sending its data over the cellular airwaves to the database online throughout this whole time. When I looked at the spreadsheet later that day, I couldn't help but notice that power production was higher while the panel was on a steep angle to the sun. To say that this surprised me was an understatement. As the days went on and the experiment progressed, I noticed that when the sun was at a steep angle to the fixed angle array, early in the morning or late in the evening, the fixed panel array was producing more power than the tracking array. In fact, day in, day out, for about 3 hours in the morning and 3 hours in the evening, the fixed panel would consistently produce more power than the tracking array, which was always keeping perpendicular to the sun. So while they would get about 14 hours of sunlight per day, for about 6 hours, almost half of the entire day, the fixed panel would produce more power than the sun tracking array. Now, this of course brought the daily average for the fixed array way up relative to the tracking array. Now, this raised questions about the value of these complex systems that turn these massive solar arrays to face the sun. They are mechanical and therefore prone to failure, and they are an added expense. In like spirit of the MIT research, a tracking array by necessity has a larger footprint because the panels move. All of this factors in when considering whether or not it is worth installing tracking on your arrays. But this serendipitous discovery also led to the third and final experiment. It would seem that light hitting the panel at a steep angle produces more power for some reason. This would seem to corroborate what the MIT researchers discovered as well, seeing as how they deliberately put their panels on an angle to the sun, but for different reasons. So what would happen if I modified the tracking panel so that rather than keeping the array perpendicular to the sun, it instead maintained a steep angle? Now, because this experiment was not at all on my radar originally, and because I was modifying what I already had, my modifications were limited and frankly clumsy. But it would be a proof of concept, hopefully, because the array could only turn about 90 degrees or so, and the panel had to start off the day at a completely different angle now. I rotated the base in order to orient the panel rotation better. Now, I realized this actually set up some pretty complex geometries because the panel was angled 45 degrees backwards from the base, and now I rotated the base relative to the sun. But that shouldn't matter much for this proof of concept anyway. So repurposing and remounting the photosensor array like I did also caused complications with weird shadows from the panel landing on the sensors. This was especially problematic at first light, as the array wanted to point directly away from the sun, not into it at, a steep angle. Obviously, the whole point of this experiment was what would happen on sunny days, as cloudy days would make no difference. I managed to get 2 more mostly sunny days where I was able to data log most of the day. I took sample groups from the same times on different sunny days where the sun tracking was functioning as normal. Day 17 was the last day I ran the panels, and maintaining a steep angle of about 30 degrees to the sun, it produced a little more than 2% average over the next best day, which was day 14. Day 15 was also a day the tracking was maintaining that 30-degree angle to the sun, but as you can see, it was fairly sunny, moving to partly cloudy as the day progressed. Day 2 was a decently sunny day, but the worst of the sample group, and the angle tracking array produced about 20% more power production on average during this time period. Notice that even at high noon, when the sun was at its peak brightness and the original tracking array was normally perfectly perpendicular to the sun, the angled track still produced more power than any perpendicular tracking day. It was producing 1.2% more power than the next best day and 3.7% more power than the worst day that had bright sun at high noon. It was quite awkward to repurpose the tracking array to track the sun at an angle. At sundown, the sun was still hitting the panel at about a 20-degree angle, so it certainly served its purpose and verified my suspicions in the experiment. But this led me to wonder about a custom-designed computer-controlled tracking array that would simply measure where the sun was in the sky and steer the array so that it was always at a designated steep angle, perhaps changing which direction it faces midday. This could even just be programmed as we would know at what angle the sun was at throughout the day. Funny enough, while the angle tracking produced some of the highest power production numbers of the entire 17 days, it was not the highest. The highest numbers the tracking panel produced were, oddly enough, on overcast days. But they were colder days too, so that may have played a role. We are talking about mere millivolts here. So this led me to one more running experiment and a short experiment conducted with different solar panels. I disassembled the accordion array and built it into an inward-facing V-panel array, which would track the sun and maintain the solar panels on a 20-degree angle to the sun. Consequently, because the panels are facing each other, they will also collect reflected light from each other so that it is not lost. I also ran some quick experiments with multiple kinds of solar panels, trying to replicate what I saw in my arrays. I don't understand why the experimental arrays would produce more power when on an angle to the sun. Perhaps the crystal structure in the cells themselves is causing this? I don't know. All I know is I can definitively say that the individual panels, with no alterations to the array or the attached electronics, would produce more power when it was on a steep angle to the sun. The different solar panels I experimented with midday sun all showed an immediate decrease in power when they weren't perpendicular to the sun. With the experiments run on the V panel in bright sunlight, the power production was on par with the other two panels. In fact, it was a touch lower than both the static and sun tracking flat panel arrays. However, this difference was well within the bounds of experimental error. All the resistors I used were 5% tolerance, for example. And the difference in power production between the V panel and the tracking panel was typically around 0.7% difference. So that difference can easily be explained away by just resistance variations in the load resistors and the voltage divider resistors. So the V panel array certainly did not provide any major benefit over the sun tracking or the static flat panel array. So what am I concluding from all of this? I'm not seeing the same results from the systems the MIT team experimented with. Even if I had lined the backs of my arrays with the equivalent solar cells like they did in their experiments, I doubt that the results would change my opinion here, especially in light of their examining these arrays from the perspective of footprint size. Obviously, you can pack more solar cells into a smaller footprint when you stack them vertically and back to back. And with the price of photovoltaics coming so far down, you want to cover every available square inch in photovoltaic panels, especially in urban environments where space is severely limited. But I'm not limited in space here, and I'm not seeing an improvement in overall power production. In fact, what I'm seeing is a huge power loss with these 3D photovoltaics. What did surprise me, though, was that the difference in power production between static angled arrays and much more complicated and expensive tracking arrays was virtually negligible. Certainly, if you're taking into account the low price of photovoltaics, you are much, much better off to take the money you would normally spend on the tracking mechanics and instead spend it on more solar panels. You would significantly increase your power production for no extra cost, especially when you start to take into account the power consumed by the tracking gear itself, something I did not take into account in these experiments, because that tracking gear consumes power from your total power production and would probably drop your remaining power below that of the static arrays. You would also remove a whole mess of maintenance, as the tracking systems involve mechanical systems which can fail, as mechanical systems are wont to do. Lastly, it would appear that even when the sun is low on the horizon, the static array was producing more power than the tracked array anyway. So, as a result of all of this research, I will now be confidently setting up my 10 kilowatt array as a static array, knowing that that is the best option. So, if any of you guys conduct any experiments like this, I would like to hear about it. Please let me know about it in the comments. And you know the routine: like, subscribe, hit the notification bell, yada yada. Do check out some of the other science shorts I have on this channel, and above all, have a great day and keep on sciencing.